A car sound has an intensity of 50 milliwatts per square meter when it's measured 2 meters from the horn. First part of the question asks, how many decibels is this? So there's a formula we can use to convert intensity to decibels. The formula is D equals 10 log of I over IO, where IO stands for the intensity of the threshold of sound. It's 10 to the minus 12 watts per meter squared. That would be the intensity of just barely being able to perceive a sound. Now, the intensity we were given is called I, and this is in milliwatts per square meter. I'd like to convert that to just watts per square meter. The M here stands for the prefix milli, and milli is 0.001 of something, or 1/1000th of a thing. So I'll convert that intensity to regular watts, and we'll do that by multiplying. There's 0.001 watts in every milliwatt. Therefore, this is actually 0.0500 watts per meter squared. All right, what I can do next is I'm going to plug in to the formula. We'll put my 0.050 on top and put 10 to the minus 12 on bottom. And we just have to enter that into a scientific calculator. Log is a button on the calculator. And we can use the caret to put the -12 power on. And that should do it. It's 107 decibels. Next question is a little more complicated, though. It says, how many decibels would be heard from this same horn if we were at double the distance away from the horn? We're now 4 meters from the horn. All right, so if this picture here represents a vehicle, and there's a horn blasting, and we're standing 2 meters from that vehicle, the sound has to spread out amongst not just a circle, but in 3 dimensions, it would be a sphere. The sound energy has to radiate out in all directions. So what we have to figure is that the energy is going to be distributed amongst a sphere of area 4 pi r squared. That's a geometry formula for the area of a sphere. And so right now we're at a r of 2.0 at the beginning of the problem, but in the second part of the problem we're going to be located at a distance now of 4 meters from that horn. That's double the distance. But the area that the energy gets spread out to now is much larger. And so the effect of that is we're going to perceive a sound that's less intense. So let's calculate what the old area was for the 2 meter distance. That sphere would have an area of 4 pi times 2 meters squared, which is 16 pi square meters. The new area is going to be 4 pi times 4 meters squared, and that's going to be 64 pi meters squared. But the concept behind the sound propagation is that it's actually going to be the same amount of energy dispersed amongst a larger area. So what we could do is take this 0.050 watts per meter squared and figure out how much energy the horn is giving off. So I'll use this formula. Intensity equals power divided by area. Now we already know the intensity for the small sphere. I'll make that the yellow sphere here. So the intensity that we heard at the edge of the small sphere was 0.050 watts per meter squared. We could find the power P if we plug in the area of that sphere being 16 pi square meters. Multiply across and we'll find the power that the horn is emitting. It's 2.51 watts. Watts is a unit of power. Now, what we have to do for the larger sphere now is figure that that same amount of power is now going to be distributed to a larger area. So we can do the intensity formula one more time. This was for the small sphere where the R was 2 meters. Now we'll do the calculation again for the large sphere. This is when the person is standing at a distance of 4 meters. And we can calculate the new intensity by dividing the horn's power by the new area. I get an intensity of 0.0125 watts per square meter. So the intensity got cut in 4. It was 1/4 of the intensity when you double the distance from the source. Okay, but now let's answer the question of how many decibels would be heard at that location of 4 meters from the horn. For that, we'd use the decibel formula. D equals 10 log of I over IO. We have the new intensity of 0.0125. And we'll put that 10 to the minus 12 on bottom. About 101 decibels. So even though we cut the intensity in 4, the decibels only went down from 107 to 101. And that's because decibels is a log scale where dramatic changes in intensity don't make that much of a difference to the number of decibels. It gives us a more reasonable scale to work with when we're measuring loudness.